Great. So, welcome everyone to one of the Otago Energy Centre symposiums, seminars, sorry. Today we have the pleasure of Dr. Ian Mason from the University of Canterbury. You're in the Civil and Resources Engineering Department. So Ian has done some really neat work on and looking at scenarios for 100% renewable energy in New Zealand. So as most of you know, we have a lot of renewable energy resources. We've got a very high percentage of renewable electricity. But what about things like heat and transport? And Ian's done some really neat scenarios looking at this type of thing. So today, Ian's going to give us a talk on a smart energy system for New Zealand. Thanks.
Well, thank you very much, Michael, and thank you all for coming today. It's great to see such a good turnout. So on the slide above us, you can see a couple of images. The one on this side represents the old order. Some creative use for the old order's infrastructure, and this one represents something of the new order, a solar tree. And both of those were taken in Copenhagen on a sunny afternoon a few years ago. And you'll be hearing a bit more about Denmark during the talk today. So the summary that, right.
Let me just make sure that you've got this switched on. There's an on-off switch. Sometimes just this.
I'll just use this.
That's it. Working out.
Oh, it's working out. Thanks, Janet. Right. So there'll be three themes going through the talk today. First one is, oops. Right. Okay. First one is to talk about a fully integrated energy system for New Zealand. And it goes without saying that this will be, if it's a smart system, it's going to be a renewable system. So I won't really argue that any further, except to take that as a given. The second theme will be to look at the idea of energy carriers, and I've identified three. I've identified electricity, heat, and fuels as three energy carriers. And the interesting thing is to see how these might interact and interrelate to each other. And then this will have engineering implications, which are very interesting to me as an engineer, but it's also going to have social implications, and there'll be political implications, and I'll talk about those towards the end of the presentation. So I want to introduce some key concepts and key ideas, and the first of these is the three energy carriers. Just to repeat that, because it's very important, it's very central to my argument today, and just to expand a little bit on the fuels. This can be liquid fuels, gaseous fuels, and solid fuels. So we're familiar with that from our existing energy system. Three no regrets. This comes from the European Union. So they adopted this as policy some years ago that whatever the outcome in the future, there was no problems with energy efficiency. And I'm not going to say much about energy efficiency except to say that that's a given. And any smart energy system will focus on energy efficiency in the first instance. More renewables, no regrets about that. And improved and more energy infrastructure, which is appropriate to the new system. And as I was writing this, I thought about the three tenors. I thought, oops. And then I thought, well, maybe I could put a photo of the three tenors in there just as an aid and memoir to the idea that there are these various groups of three ideas. And think about their wonderful music as well. So now there are three other ideas which come into this. Energy storage, and that becomes increasingly important. The more renewable, particularly variable renewables like solar and wind, and some extent hydro in the system, then the more important storage becomes. Allied with that is the idea of energy spillage. Now, if we have enough storage in an energy system, there'll be no spillage. But sometimes there's not enough storage, or sometimes it's too expensive to have enough energy storage. And in some cases, we might even want to design a system deliberately to have spill. So that's something I'll elaborate on a little bit further in the talk. And the third of this last group, energetics, a way of evaluating the success of the system. So I'm not going to talk about economics as a way of evaluating the success of the system. As an engineer, I'm interested in the laws of physics, the laws of thermodynamics, and how they relate for our assessment of the system. So that's what I'll be focusing on. I want to have a closer look now at our energy resources. Now, in the left-hand column there, you can see the main ones listed. So we've got solar, wind, hydro, biomass, geothermal, and the key conversion technologies there. And what I want to do is look at the energy products from each of these. So firstly, solar thermal produces heat, generally low-grade heat. Solar PV and concentrating solar thermal produces electricity. Wind, electricity. Hydro, electricity. Biomass is interesting because it gives us a variety of options, but electricity is one of those. We can produce hot gases by burning stuff, and we can get liquid and, in fact, also solid fuels out of the biomass resource. The wave and the tidal machines can produce electricity, and geothermal gives us electricity and heat as well. So there's one overwhelming theme coming out of that, electricity. And if we weight this column for the size and availability of the resource, electricity still comes out on top. So the first argument I want to make to you today is that any sustainable, smart energy system in the future will be based on electricity. To quote Transcar, the future is electric, and I agree with them. There will be a role, of course, for the others there, the heat and the fuels part of it as well, but I believe that energy will be the dominant energy carrier of the future. In terms of energetics, we have this term called energy returned on energy invested. And you may remember from some years ago, people talked about making ethanol from corn and how it didn't break even on an energy basis. I think those days are gone. As anybody that's worked in this field knows, this is derived from life cycle analyses, and that's fraught with difficulties. It depends where you draw the system boundaries, what sort of data you have, and a whole lot of other factors that go into that analysis. And what it means is you can get a very wide range of figures for the EROI values. So the Americans talk about energy return on investment. I like to be a bit more specific, energy return on energy invested. But we need to take this with a grain of salt, but there is a general trend. And that is that, generally speaking, hydro is better than wind. Wind is better than some of the biomass conversions. They're better than geothermal to electricity, and that's better than PV, and that's better than other biomass. So going back to the laws of physics, it really behoves us to use the technology and the resource with the highest EROI value, if we have the choice in order to do that. Now, there are other factors involved as well, such as greenhouse gas emissions and land area requirements, which can tweak that order somewhat. So generally speaking, I'm going to go ahead on the assumption that this is a sensible order of choice of technologies to make. So what's a smart energy system? So I'm going to take the definition from this paper by Danish researchers, Mathisen, and you might know the name Henrik Lund. He's been kind of the grandfather of energy systems research over the last decades, so a really powerful figure. And very interestingly, he's in the Department of Planning at Otago. He's not an engineer as such. But I think this is one of the most important papers that's appeared in the energy literature over the last 10 years. And their definition of a smart energy system is this, and I'll just read it out so we can get a good feeling for what it is. So it's a design in which smart electricity, thermal and gas grids, so emphasis on the grids, combined and coordinated to exploit the synergies between them to achieve an optimal solution for each individual sector, but also for the system as a whole. So that's what really interests and excites me, is this idea of optimizing the interactions between these various energy carriers. The Danes have been working on this for a number of years, since about 2006. They really got serious about being free of fossil fuels by 2050. That was their idea. And that's still government policy in Denmark at the moment. And their Climate Commission reported in 2010 and came up with this diagram. And I'm not going to go through it all in detail, but there's a few key things to note here. First, wind is electricity from wind is one of their primary energy resources looking to the future, and also using quite a large amount of biomass. But also we can note there a little bit of wave, some solar panels there, some solar thermal there, use of heat pumps, use of geothermal. This is combined heat and power plant, so that's electricity plus heat output. large thermal storage, there's very large hot water tanks, basically, using district heating in built up areas, industry being part of it, and electrification of transport to some extent as well. Now, there's one key thing in here which just want to focus on, and that's that Denmark, of course, has a land border with Germany. It's close to Norway and Sweden, and they're even talking about building an HVDC cable across to the UK. So they can balance their electricity system easily by importing and exporting electricity with other countries. They use Norway as their storage system. They sell cheaply to Norway, and then the Norwegians sell it back to them at a high price. That's the beauty of the market, I guess. So that's just to give you a flavour of what a smart energy system might look like and what the components are. Now, a little bit more detail. Here's a system with 75% wind penetration and a box labelled fuels. And this diagram firstly shows the three grids which I talked about earlier, the electricity grid in black, the heat grid in red, and the fuels grid or a gas grid in yellow. So, just have a quick look at the numbers. There are 39 units of wind electricity being produced. 30 of those go to conventional electricity demand, but some of it's siphoned off. We have 10 going to the heat pump group and producing heat from there. We have 8 units going to fuel synthesis there, and 4 units going to transport for electrification vehicles. There's also another 13 units coming in from the CHP plants. So if you add those numbers together, we've got 52 units going in there, and if you add the other ones up, you'll see that it all balances, and we've got the same number of units going out. So already we can see this idea of a smart energy system taking place, where some electricity is siphoned off into other parts of the energy system. And there are reasons for doing that. So coming back to CHP, we've got 11 units of heat going to the heat sector there, and this heat pump, a coefficient of performance of 2.9. That's one of the smart ways of dealing with surplus electricity, is to put it through heat pumps and put it into the heat sector. And then if we look at the fuels, we've got the bulk of that going to CHP plants. They produce, as I said, 11 units of heat there. And then the rest of it's going into fuel synthesis. So there's a lot of bits in the process missing here, if we just bear with me for the moment. And that's producing 16 units of liquid or gaseous fuels going to transport sector, plus the 4 units of electricity going in there. Now, 16 and 4 is 20, which doesn't equal 30, but there's a different deficiencies associated with electric vehicles, of course, and internal combustion engines. So if you put the efficiencies into that, it all adds up to 30. The diagram on the left just exposes the 3 grids and without all the other detail in it there, so it's just a little bit more visible. Over here they've added in storage, so we can see there's some storage of solid fuels. That's something in the old fossil fuel system. We have piles of coal or tanks of gas available to dispatch at our convenience. There's some gas storage in the system as well. We've got thermal storage and some liquid fuels and some battery storage in the electric vehicles there as well. Now this is for Denmark. The highest point in Denmark is just about 200 metres, I think, or maybe a little less. So as I said, they use Norway as the storage system. In New Zealand, we're lucky. We've got a very large battery called the Hydro Lake. It's about 4,000 gigawatt hours available. And so that's how we can balance our electricity system in large part. So that's the general idea of the smart energy system and the idea of the interactions between the various sectors. So Matthiessen and company's research produced this diagram, and I'm not going to go through all the detail and all the numbers. Just firstly draw your attention to this left-hand column here. So as I said earlier, their idea is to have wind and biomass as the major inputs into their energy system. So we've got biomass there. So the thickness of these lines represents is proportional to the size of the resource. And so biomass there, wind there. A little bit of biogas production, that's mainly methane, of course. A little bit of PV, a little bit of wave, a little bit of geothermal, and a little bit of solar thermal. So those last categories, they make up very much individually, but you add them all together and they become quite a significant part of the whole mix. So it's worth thinking about those because of the accumulative effect. And then, oops, let's go back. And then over on the right-hand side, we've got the transport sector, the electricity demand, conventional electricity demand, and then heat demand over here. There's various numbers here in terawatt hours if you'd like to have a look later to actually see how it all adds up. So I wanted to draw your attention to some of the key conversion technologies which allows these interrelationships to happen. So firstly, electrolysis. So this is taking surplus electricity and producing hydrogen from that, and then feeding that into electrofuel synthesis. Gasification of biomass is important, so that the product of that initially is producer gas, and from producer gas we can develop syngas, which is carbon monoxide and hydrogen, and that can be the building blocks of the various synthetic fuels. So one route is to take products, carbonaceous products from gasification, hydrogen from electrolysis, put it through, in this case, the that's a bio route, so that's using microorganisms, metabolic pathways, in order to produce these materials, and that goes into the transport sector. Now, there are other means of making electrofuels. Some of you will be familiar with the Fischer-Tropsch process, which takes syngas, and that was, of course, used in Germany during the Second World War, and also in South Africa during the apartheid regime. In fact, I think they still use it in South Africa even now, the Sasol process. And combined heat and power plants are a key feature of the Danish system, and as we've seen, along with district heating and heat pumps. So that's the idea of interrelationships being quantified and the relative size of the resources in their particular idea. So I want to leave Denmark behind now and come to New Zealand and see, well, what are the prospects for us to start thinking about such a system. So how do we compare with Denmark? Well, we've got much better solar and wind resources than they have. We've got a milder climate, we're a bigger land area, we're a slightly smaller population. So if the Danes can do it, surely we can do it. But we do have some disadvantages. We're not linked to any other country in terms of electricity. Although I believe people have talked about an HVDC link to Australia, but well, they have telecoms cables, so why not? But that's a long way off, if ever. We tend not to have district heating. We have it in hospitals, we have it in universities, but we don't have it on a big scale. So that with combined heat and power probably isn't something that's going to work well for us, at least not with our present infrastructure. We have a gas grid in the North Island, but not in the South Island. And one of the things the Danes really cottoned on to was the economic opportunities to develop new industries, expertise, and products, and sell those to the world, and they've been quite successful in doing that. But we're a long way from markets, so we have to think seriously about what we can actually produce. And what expertise do we have on which to build, which the Danes and the Germans and the others which are really leading the charge in this area, that they don't have. There's a new wind farm, offshore wind farm being planned off the coast of Victoria in Australia, and already the Danish engineers are out there doing the work. So we've got quite a long way to go, I think, to build the expertise. We have some in geothermal, but what else do we have? It's a question mark. In New Zealand, we have some new policy directions with the election of the new government last year. And firstly, the Zero Carbon Act is being discussed at the moment. There's a Climate Commission on the way. So that's a positive sign. Transition to 100% renewable electricity is now part of the political narrative, which it wasn't 10 years ago. And there's talk of an investment fund, $1 billion to cultivate and encourage new industries. So now I want to look in just a few figures and see where is New Zealand at the moment in terms of fossil fuels and renewables. And I put the supertanker there. One supertanker can carry 10 to 12 petajoules of energy. So New Zealand's primary energy use is about 900 petajoules per year, and as you can see from the pie chart, I think it's just disappeared. But anyway, you can, if you look at the fossils on the left-hand side, you can see they're about 2/3, and the renewables are about 1/3. So it's about 60-40 in 2016. So we're still 60% a fossil fuel country. In terms of delivered energy after the energy conversions, then it's still pretty much the same picture here. Still dominated by oil, mainly in the transport industry, some coal, some gas. And you see the geothermal has really shrunk there. Some proportion that's gone into the electricity sector, so that 1% is just the heat that's used in geothermal applications in some parts of the country. So that's where we're starting from. In terms of the electricity sector, we've been quite highly renewable in the past. I think if you go back to the 1950s, we were 100% renewable at times there. And in 2016, we produced about 42,000 gigawatt hours of electricity, primarily from hydro, with a large proportion from geothermal, and large proportion from gas, and then minor contributions from the other bits and pieces of renewables, etc. So that all adds up to 85% renewable electricity and 15% on fossil fuels. What we're seeing now is a move towards 90% and over 90%. My own argument is that 100% renewable electricity is well on the way. It's happening. There's a little bit of fine-tuning to do, but it's really not the major challenge which we face anymore. So I'd like to talk about some arguments which were put forward by us some years ago as to whether we could have 100% renewable electricity. And I'm doing this as a basis for a largely electric energy system. So if we can get the current electricity sector 100%, then we should be able to use that information and that knowledge to get the energy sector close to 100%. So we studied for 6 years. It took data at 30-minute intervals and removed all the fossil fuel generation from the energy mix in the electricity sector, and we added in wind and geothermal. There's a number of assumptions in the study. First, that the whole system is centrally planned and operated, and that the single goal that people had was just to make the best use of the energy resources, and that included minimising spillage. So there's no market involved in here. We varied the hydros in response to the availability of wind. So when wind was up, hydro was down, and vice versa. So that was varied from the historical way that the hydro lakes were operated. And we treated the hydros as one big bucket. And the argument there was that they're not connected geographically, but they are connected electrically. So that seemed like a reasonable assumption. A PhD student at the moment has actually separated the North Island and the South Island storage in order to get a more fine-grained analysis. And this is a backcasting study, so we have perfect information. This is the historic energy mix from 2010, and it's pretty much the same story that we just saw before in the sort of overview of New Zealand. With our 100% model, we found that hydro was producing pretty much the same amount, but there was a vastly increased amount of wind. There we go. There, a lot more from geothermal, and the biogas and the wood thermal were just as they were. They weren't altered at all, so they're still very, very small contributors. What do the generation patterns look like? So this is a historic pattern of generation from firstly the hydros. This shape here, which looks like a tooth, that's just a 24-hour profile of electricity generation by hydro with the morning peak and the evening peak there. And so that's load following. Then the coal, the gas is load following, the coal is load following, the geothermal is operating as base load, not varying too much. And the wind there is doing its own thing, varying around at that point. So with the 100% renewable operation, this is what's happening. And the first thing to note is the hydro in blue is operating over a much, much greater range than it did historically. So it's reaching its limits about that point, and it's bottoming out at its lower limit at that point. The wind is in green, and you can see that's much increased over the historic profile. And if you look carefully, you can see that when the wind is down, the hydro is up, and when the wind is up, the hydro is down. So that's just the two responding together. And that's a very well-proven system in some parts of the world. And the geothermal is increased here, and we just operated that at constant base load. Now, geothermal can be dispatched, and I'll talk about that just in a moment. In a system like this, there will be periods which produce surplus electricity, and there'll be other periods which produce deficits. So those have to be satisfied. So these deficits here have to be satisfied. Now, if we're lucky, the amount of surpluses will exceed the amount of the deficits, and we can use those surpluses in some kind of storage system in order to supply the deficits. So let's see. So this is over 6 years. This is the cumulative surpluses over 6 years in gigawatt hours. This is the cumulative deficits. So we can see, yes, there was plenty of surplus there. So we modelled the pumped hydro storage system with over the 6 years, and that had a capacity of 368 gigawatt hours. That's just under 10% of the total hydro storage we have at the moment. But the interesting thing, and I guess slightly concerning in a way, is the very high capacity required. So that's because there's periods when the generation has to ramp up very, very quickly and over a very large range when the wind drops off, or when demand increases, or if it does both at the same time, then you can't control. As alternatives, we looked at demand-side management to see whether that could alleviate some of this peaking, and it could do some of it, but not all of it. The other option is to just abandon the 100% renewable idea, and we calculated that it would be 99.8% renewable if we use fossil gas in gas turbines as a way of meeting these deficits. And so I've argued, and I continue to argue, I'm not too worried about 100% versus 99.8%. The truth is that not very much gas gets burned. So we need to maintain the fleet, but we don't burn a lot of gas. There are some commercial challenges around that, but people are starting to talk in that way. There was an item in Energy News just recently arguing the case for gas. So I think that's definitely an option, at least as a transitional measure. Now, it's a lot of information in this slide. I won't spend a lot of time on it, but this is firstly over the 6-year time period. The dotted line at the top represents the capacity of our hydro lake storage system. This dotted line here represents what used to be called the min zone. So that's the level of storage in the hydro lakes which is required to be maintained to prevent future shortages of electricity. So you can see that sometimes at the year you need a much higher reserve than at other times of the year, and that's just because of the predictions about hydro inflows over the subsequent period. Now, there's a very light grey coloured plot here, and you just look here and here. There's 2 occasions when it flatlines at the top, and that means that there's energy, there's hydro water being spilled out of the hydro system. It can't be accommodated anymore. So we were interested in whether we could minimise or eliminate that spill of water. It did raise the interesting debate, which I think is current still, of is it better to spill water, or is it better to spill wind, or is it better to spill some other energy resource? And, that's not really resolved. But one thing we can say about geothermal is that that geothermal resource can stay in the ground. You can turn off the valves and not operate, or operate at a lower output, and you can save that resource for another time. So we're renting it on that. And this represents the operation of geothermal when it's on, and the gaps are when geothermal is off. So you see the geothermal is off just before those spill events. Yeah. Off, 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 off. And that meant that now the result from that was the black line. So what happened then, when the geothermals were off, the hydros came in and pulled the lake levels down. And we were able to model it so that the hydro lakes just reached the capacity once, and there was no water spill. The other thing to note is that 2008 was considered in our study. It was the driest hydrological year on record up to that period, and our system guaranteed security of supply during that time. So at the end of the day, we were left with this, no deficits, which were taken care of in our case by the pump storage system, and a small amount of surpluses. Those surpluses, of course, just represent curtailment. You can't have surplus of electricity just sitting around. It's got to be curtailed. Okay, so the argument to this point is that there's good evidence that we can have, at a 30-minute resolution, 100% renewable, or very close to that electricity system. There are some issues around at the sub 30-minute level which need to be addressed, and I'll just mention those briefly later on. But the next interesting thing to consider is whether the storage can be reduced and the whole system can be optimized. In this graph, the storage is normalized here, just going from 0 to 1 here, and this is over a period of 1 year. And this is a modelling exercise actually on a household, but the principles are exactly the same. Now, penetration of 1 is where the generation installed, in this case PV panels, produces exactly the demand of the house. And then another 11% for the losses going in and out of storage. And in that case, this is the storage profile over a year, and so this is its peak. So that's about 35% of the annual demand. So for a house that uses 9,000 kilowatt hours of electricity a year, it would need 3,000 kilowatt hours of storage. And if you know anything about the cost of Tesla batteries, etc., that's an enormous sum of money. So can we reduce this? If we put in twice the number or 3 times the number of panels, then the storage required goes down dramatically. And that's because it starts to shave off some of those deficits and makes them a lot less. But it produces still. So an optimized situation, the profile would look like this. And this represents spill, where it flatlines along here. This is where it bottoms out. And then this is around September, and then it creeps up again. So that's something. So I'd like to argue that that's an idea which could be built into a smart energy system of the future, to over-specify generation in order to actually optimize the whole system. Evaluating this, here we've got the energy invested, and I won't go through the whole of this graph, but we'll just look at the top graph, which is the system. So the energy invested in the combination of PV panels and batteries, in this case, bottoms out at a penetration of about 2.5, and then it's like it climbs up as you build more and more panels into the system. Evaluated in terms of energy return on energy invested. Firstly, 1 is the break-even point. And so the optimum here is about 2.5, 2.6 in terms of EUR. So that justifies it from an energetics point of view. You'll also note that these values are actually quite low. When you bring storage into the equation, it actually drops the EURs. PV, it might be about 5, 6, 7, 8, 9. But if you add the storage in, it drops down considerably. So, at the end of the day, with the high renewables in the system, we're left with periods of time when there'll be surplus. So what to do about it? We can use that surplus electricity to produce hydrogen and then put it through a fuel cell back to electricity. A lot of researchers, including myself, don't favour this route because of the very low round-trip efficiency. We can use hydrogen as an input into electrofuels production, as we saw in the Danish scenario. We can use hydrogen directly as a combustible fuel, and we can maybe inject it into the gas grid, as they're doing in Northern Europe at the moment. Or thermal storage via heat pumps, which we saw in the previous slide. Just thermal storage in hot water tanks, which we saw in the Danish pretty picture. Or curtailment. And so there's an interesting study, I think, to be done, storage versus curtailment, which is there an optimum point at which you curtail versus when you actually use it in some way or other. So this is a diagram from a North German company, which is taking surplus wind electricity, putting it through an electrolyzer. Wasserstoff is the German word for hydrogen. That's been injected into the gas grid and sold to customers as wind gas. And that's going on in many parts of northern Germany at the moment. So, can be done. Now, what about the question of 100% renewable energy? So moving now from electricity, the next topic is energy in total. And here we've got an industrial process. Here we've got, this is a cutaway of a Nissan Leaf, and that shows the battery pack in orange. So the idea here is to look at stationary energy and transport. So this is another study that we did, just looking at 1 year, and we did this in the context of the Paris target for New Zealand's greenhouse gas emissions. So as many of you know, New Zealand government has signed up to reduce our emissions by 30% below 2005 levels by 2030. So 58.6 is the number, which is also 11% below 1990 levels. Business as usual scenario, about 89 if nothing happens. So that would mean a removal of about 30 megatons of emissions from our profile. So this was one of the results of our study. So using fossil fuels as per normal, we're using this amount of delivered energy, and using electricity, we're using much lower amount of energy for these uses. This was a scenario where heat pumps were included for low level heat, and we excluded aviation, shipping and heavy vehicles. We did do a parallel study on aviation, which I'll mention the result briefly. That was a 54% reduction in energy, excluding transmission and distribution at this stage. And that was about 25 megatons of emissions reduction. Now, if we were to factor in the emissions reduction from 100% renewable electricity into that, that would come to about 30. So in principle, this could be done. We can meet the Paris target by electrifying all stationary energy and transport and completely removing fossil fuels from the electricity system. What about bioenergy? If we could use wood chips for many of those stationary energy uses, then what would it look like? We need about 39,000 gigawatt hours per year of energy in the wood chips. And just to put that in perspective, it would mean allocating about 30% of New Zealand's plantation forestry just for energy uses. Now, of course, that was just like a comparison. It's not a serious suggestion. There's a lot of other demands on New Zealand's plantation forestry. So I think a lot less biomass will actually be available in the future. Right, so what we found out of this, we'd need about another 42,000 gigawatt hours of electricity in order to cover stationary energy and transport. That's about the same amount as produced in 2014. Now, in terms of availability, there's consented and planning generation in New Zealand at the moment, mainly wind, but a little bit of geothermal. That would give us about 15,000 gigawatt hours. So we need another 27,000. And that could be provided by wind. The lower figure there is for offshore wind, about 5,500 megawatts, or 7.6 gigawatts of onshore wind. To do that by 2030, we'd have to install that number of megawatts per year over the next decade. Now, it's not impossible. Those numbers are being commissioned in Northern Europe at the moment. But for little old New Zealand, on the edge of the world, with none of the infrastructure which they have in Northern Europe, virtually impossible. So, however, nonetheless, this sort of thing, I think, is part of our future. In terms of electrification of industrial processes, just this week, Synlait announced that the Dunsandel plant, pictured here, is installing a new electric dryer. They've claimed to be swearing off coal, and I believe, though, that they're going to keep using gas in the North Island. But it's a start. And already the lines company's working on the upgrade of the system and transformers to make this possible. And I believe, my memory tells me that for spray drying you need about 80 degrees. So this is low temperature heat, which is easily done by electrification. So engineering challenges. So if we were to embark on this route and take it out to 2050, which is more realistic, then it's still a massive challenge, massive amount of extra electricity required, 2 to 3 times the 2014 production. This little chart here, this little column, that's New Zealand's 2014 electricity production in gigawatt hours. That's the result of our 2014 study, so that's doubling. And then our aviation study, that was based on all aeroplanes flying on hydrogen. Technically possible, has been demonstrated, and that required about 15,000 kilowatt hours.
Sorry, is that just internal regional airlines?
No, that's replacing all aviation fuel, all kerosene pumped in New Zealand. So both for domestic and for international flights, which fuel up here. So whatever fuel they take on board here. New Zealand has a wonderful wind resource, and it's the most, in my view, I would argue it's the most sensible resource for us to use in the future. And the industry is in agreement, I think. They're all saying that wind is really, really important. But it's going to result in a very high wind penetration in our electricity system, and that has a number of issues. Also, I think we need, and I argue strongly, we need to start looking at offshore wind as an option for us in New Zealand for various reasons. Some of the problems in the electricity system, taking out these big synchronous generators, such as the Huntley generators, lowers the amount of inertia in the system. Inertia is the first defence that the electricity system has against fluctuations, and so that needs to be addressed. Now, I've put in the reference list some work which is being done at Canterbury at the moment, where one of the electrical engineering PhDs has actually quantified the amount of inertia removed and looked at the instantaneous reserves which need to be added in order to cope with that. And also how much spill. We know that spill will occur, but how much and when will it occur? And another PhD student has been quantifying that, so that reference is also in the list. Energy conversion, so you may remember back to the slide where we had electrolysis and co-electrolysis and other processes going on. There's a real need for more research in that area, particularly to improve the efficiencies and to look at the real-time operation of those systems. Storage, the role of bioenergy, and the build rate out to 2050 are all important challenges for the engineers to get to grips with. But I think in any event, we need to get used to more sites like this as possibilities in our seascapes in the future. This is just off Copenhagen, looking out towards Sweden. And this is quite a small wind farm. I think it's only about 40 megawatts or something like that. The turbines are now much, much bigger than that.
What's the acreage?
Sorry?
What's the acreage for a farm like that?
I don't know for sure. I think the important thing about wind farms is that whatever land the wind farm occupies, very, very little of it is actually taken out of use. In fact, farmers get paid royalties for having a wind farm on their land, and then they can graze the sheep or put the animals under there or even grow crops. So it doesn't take the land out of production. It just has two uses instead of one. Okay, so those are some of the engineering challenges that I see ahead of us if we move towards a smart energy system, but there's some social science issues as well. And I think there's a need for some scenario reframing in terms of the way we approach people's reactions to this new infrastructure. So I would argue that we're going to need more wind turbines and more pylons on the landscape. And normally when we discuss with people or survey people, it's, do you like this view without the wind turbine, or do you like the view with the wind turbine? I don't think that's appropriate anymore as we face the impacts of climate change. I'd like to see experiments done where people are asked, do you like this? Or do you like this? Or do you like this? Which one would you rather have? Or would you rather have your electricity distribution system collapsing on a regular basis and having electricity outages? Now, that's not as simple as it sounds, but I think it's something we can work through with the social science community. I think another big challenge, and some of my best friends are social scientists, but I have to say that they're very good at explaining what's wrong and telling you why it can never be different. But the environmental psychologists are really good at designing interventions and how we can change people's behaviours or reactions in a positive way. And social comparison is one of the most promising in the literature of all of these approaches. So I'd like to see more focus on interventions to bring people around to the realities which are involved here. I think it's really important to start considering the the economic paradigm in which we're evaluating our systems. You might remember from the beginning of the talk, I said I'm just going to talk about energetics and not economics. And that's because I'm not sure that the economic model we have at the moment is fit for purpose. And I think we need to be reading more about the works of Herman Daly, father of ecological economics, Brian Check, steady state economics, Steve Keen, author of Debunking Economics, and Kate Raworth, whose book Donut Economics came out last year. And I like Steve Keen because he said of all the people, well, he said, the last people you want to trust for the future of economics are economists. He said people like engineers and other scientists and people trained in those areas of systems thinking are the people that should design the new economics. So he's got my vote. This focus on eternal GDP growth, GDP as a measure of success, etc. The very idea that impacts on our Earth system or impacts on society or externalities is almost mind-boggling when you think about it. Are there externalities and just put a price on it? Well, I think they're internalities, and that's demonstrated in the next diagram, which I've appropriated from Kate Raworth. And firstly, it puts economy nested within society, and society is nested within the Earth system. So what I really like about this, and I argue that this really represents the real world, is that the Earth system is the big system, and society relies on the Earth system, and the economy relies on and services the society. From an energy point of view, solar energy is our major flux. Sorry. We have some small contributions from tidal and geothermal. And coming back to the laws of physics once again, we know from the second law, that the entropy law, that this is inevitable, that there'll be a discharge of heat back into the universe again. You might be wondering where wind, solar and the others are. So wind, hydro and biomass, all second-hand solar. Wave energy is third-hand solar, so it all relates back to solar. So they're all in there. And of course, the problem that and the challenge that we face is we have this insulating blanket with the warming temperatures. In terms of the economy, of course, traditionally it's been a relationship between businesses and households. That's how it's traditionally portrayed. But I just draw your attention to the inclusion of the commons in this particular model, which is why I think it's particularly appropriate for us going forward. I think this is not a good paradigm to be going forward into the future with. You might recognise this diagram. This is what Paul Samuelson drew back in 1948 in order to educate engineers about economics, because they hated the approach prior to that. And you can see it's designed for engineers because there's a tap, and there's some pipes, and there's some tanks, and there's a bit of an outlet there, and there's some stuff going around in a circle. So you can see why it was appealing. Here's a more modern version. Relationship between households and businesses, the idea, with trade, government and banks either giving injections or receiving leakages. And particularly important to talk about labour and capital. Now, labour and capital are considered the two factors of production in neoclassical economic paradigm. The land used to be in there, and the classical economists had land in there as well. It was kicked out for quite some, I think, dubious reasons. But I think the key thing about this model of the economy is that there's no connection with the physical world. There's no connection with energy. There's no consideration of the laws of thermodynamics. And I struggle to see how this is compatible with the ideas around a sustainable future. So that leads on to some policy challenges. First thing I'd like to see and argue for is a fully integrated energy policy, which aligns with the idea of a smart energy system. And instead of energy in silos, we have energy interrelationships and things connected together and flows going between the various sectors. The electricity system is governed by the Electricity Authority at the moment, and that has very limited responsibilities. It's just tasked with keeping the market in order and keeping the market functioning smoothly. If one was to go back and look at the Electricity Commission which preceded it, then that had a much wider scope of responsibilities. And I think there's a good argument for returning to that model as we move forward. It would be interesting to look at the idea of a storage market in addition to a full energy market. Storage is becoming much more prominent now as people, say, put PV panels on their roof, but they want to stay grid connected. So they're actually using the big battery in the hydro lakes, but they're not necessarily paying for it. So they don't necessarily know that it's actually part of their operations that's keeping it going. So I'd like to see that addressed. And let's seriously critique and have a proper grown-up discussion about whether the neoclassical economic model is really fit for purpose in the world which we face. So what next? First thing I'd like to do as a systems engineer is model the whole of New Zealand in the same way that we saw previously. This is a Sankey diagram, it's called. Produced one of these for New Zealand at very fine resolution. I'd like to see more discussion around the framing of social science experiments and a focus on developing appropriate policies. And let's continue the conversation. So just before we do, I just want to acknowledge some important people. These characters, these are some of my co-authors over the last 10 years. It's very much been a team effort. I'd just like to pay tribute to our energy students. They're always good for inspiring thoughts and asking difficult questions, which is very helpful. And a big thank you to Michael for the invitation to be here and for the Centre for facilitating my visit today. So thank you very much for your attention.